Go live. Get a little audio test going. Okay, seems to be working. Alrighty. Got the screen share going, and we've got our slide deck. Alrighty, let's get started here. So welcome to week 8 of the RoboChargers CAD class. This week for our engineering concept, we're going to be talking about material strength. So the first thing to understand is like we're going to talk about a little bit of the mathematics. I don't have any equations or anything, but we're going to talk about a little bit of the mathematics and the kind of behavior of materials as they are loaded and as they are stressed and everything like that. And it's important to understand like how we can use this in the context of FRC. Obviously, this has broad-ranging impacts to just engineering in general, but specifically to FRC, like how are you going to use this information? This stuff gets into some relatively high-level engineering that you don't necessarily need to know to build things. Like if you're just doing projects, you're building things, you're building robots even, you don't necessarily need to know this stuff until you get a little bit later in your engineering education. However, I still think it's important to kind of do a introduction to this early on. And so basically the reasons for that are, when you're building an FRC robot specifically, this doesn't apply as much to FTC, but when you're building an FRC robot, you are essentially given a budget of mass, right, of 125 pounds that you can use to build your robot. And that robot has to accomplish certain tasks on the field, has to perform certain actions, and while doing those actions, it's going to encounter, certain forces, certain impacts, certain things like that. And what you are doing when you're designing the robot is essentially you are choosing where to use that mass to accomplish the tasks and withstand the forces that you have to withstand. So basically, what this boils down to is there's kind of two cases that you'll run into. So the probably the most common case, especially for beginners, is you design something and you don't have a good understanding, you don't have a good intuition for how heavy duty you need to design your thing, right? And you'll build the thing, you'll design the thing, you'll build the thing, you'll test the thing on your robot, and then the thing will break, right? Like you will have under designed the part that you needed, right? And so, in that case, an understanding of kind of the stresses and how the material would behave would have helped you figure out whether or not the part you were designing was going to be strong enough. Now that is the case, right? But there's actually the opposite case, and in some ways, I would say the opposite case is at least equally common and possibly more common. And it's where you get you get kind of a sense of how much material you need, or you've experienced the failure of having a part break on you before, and so you bulk up your design, you add a lot of material, you make it out of steel instead of aluminum or something, or you add a lot of mass at your to your part to keep it from breaking, but then it turns out that that part is way stronger than it needs to be. It will never fail, but it also weighs 3 times as much as it needs to. And then because you've got that weight on your robot, that is extra weight that your robot has to accelerate when moving around on the field. That's extra weight that your mechanisms have to lift up and down or move around, and that's additional weight that you can't use for something else on your robot. So basically, understanding material properties and how those properties relate to materials and parts that are being put under stress helps you design parts that are well optimized for the task that they're supposed to be performing. And then the other part of it too that is just as important as that is that there are different ways that parts can fail, very distinct ways that parts can fail, and it is important to make sure that the failure mode matches the application for that part. I will go into a little bit more about what that means later, but basically it means that sometimes your robot will take damage on the field and parts will get broken, they will get damaged, they will get permanently deformed or whatever, and ensuring that the way that they fail is appropriate for what that part's function is also sometimes just as important as making sure the part doesn't fail in the first place. So we'll talk about that a little more later. All right, so we're going to talk about a lot of concepts here, and so I kind of want to give this little introduction to kind of the context of how we're going to be talking about loading parts. So the first thing to understand is when we're talking about stress and the strength of materials and some of the properties that you can the numbers and the kind of quantifiable statistics about a particular material. When we're talking about these things, the easiest way to understand it is when materials are being stretched. Okay, like when we're pulling on a material, that's called tension. And when we're talking about the strength of a material, we're talking about tensile strength. I'll get a little more into those terms, in the subsequent slides here. But understand that in general, we are going to be talking primarily about how strong materials are when you're pulling on them. Compression follows a lot of the same rules that we're going to talk about. However, compression kind of complicates the issue a little bit because there's some other failure modes related to buckling, which I may go into a little bit later, but I really want this to be a very, very basic high level kind of discussion about this stuff. And so I'm not going to go into compression as much because there's some other factors that complicate compression. So we're going to be talking about materials in tension, and those concepts of tension will give you a good overview of the way that materials behave under load, and then you can kind of extrapolate that out to other load types. So when we're talking about tension, what we need to know, essentially, if we've got a very simple part like this part I'm showing over here on the right side of the screen, we've got this very simple part. It's a cylinder, right? And these arrows represent the way that the part is loaded, right? It's being pulled apart. And when we're talking about the strength of a part like this, we want to know what the cross-sectional area of this part is. Now, I mentioned earlier on, I don't have any equations. I think it's best to approach this, because this topic is pretty high level, or like this very quickly goes into some pretty advanced engineering stuff. I don't want to overwhelm you guys or make you guys think that you need to understand this stuff at all to be able to participate in FRC, because this, like I said, this very quickly gets into some advanced engineering stuff that you won't need to know until like your, third or fourth year of university or something. So the thing to understand here is that when we are talking about the strength of a part, this cross-sectional area, right, if I take a plane and I cut the part and the plane is perpendicular to the direction that I'm pulling the part, and I measure how big this area is across the part, that is basically going to, that's going to be an important quantity that we're going to talk about a little bit later. So that, just keep this in the back of your head, this cross section. I might refer back to this slide if I need a little more visual explanation. But this part could be anything. This part could be a square, it could be a rectangle, it could be some funky shape, it could be a cylinder, it could be an ellipsoid, it could be anything. The other thing too is if you've got some complicated part that's got it's maybe thicker at one end and thinner at the other or something. Generally speaking, when you're talking about the strength of a part, you want to evaluate the thinnest section possible, right? Because intuitively, as I'm sure you can expect, the part's going to break at its thinnest point. So when you're evaluating the strength of a part, thinking about the thinnest area is what you're going to want to do. So just kind of keep this image in the back of your head as we go forward, and I think it'll help you get a little bit of a more intuitive understanding of some of the things we're going to talk about. Okay, so let's talk about some terms here. We are going to be talking about two big terms, and I'm going to be using them a lot, and so I want to kind of make sure we understand what they are. So I'm going to be talking about two things called stress and strain. Quick thing. I'm in the middle of the presentation. Jessica's trying to join. Can somebody message her and tell her how to join the huddle, please? Okay, thank you. All right, so we're talking about stress and strain here. These sound like relatively generic things, but they actually have very, very formal definitions. So when we're talking about stress and strain, these might kind of sound like the same thing, and in everyday language they are, but they have formal definitions in an engineering context. So stress is basically force, right? That's the easiest way to think of it. Specifically, it's forces that are internal to the material. So when you apply a load to a part, you're applying a force, right? And then that force is creating stress inside the material. So when we're talking about stress, we're talking about the forces that are inside of a piece of material that is having an outside force applied to it. Stress is measured with units of pressure. So when we're talking about a force per unit area, like pounds per square inch, or pascals, which are newtons per square meter, or generally because newtons per square meter is a very small amount of pressure. Generally, we're talking kilopascals or megapascals. And so if we're just kind of linking back to that last slide that we looked at, where we're talking about the cross-sectional area of a part, you can kind of understand why we measure stress in units of pressure, right? Because that force is spread out across the cross-section of a part. So just simply speaking, if this part has a 1 square inch cross-sectional area, and I apply 1 pound of force to it, the stress in the material is going to be 1 pound per square inch, right? Now, if I apply, if I make the part bigger, for example, and I make it 2 square inches in cross section, and I still apply 1 pound, well, now the stress is 0.5 or half a pound per square inch, right? And so the stress is related to both the force and the cross-sectional area. Okay, now strain is basically the amount that a piece of material moves when it's under stress. So when you're looking at materials like steel and things like that, and you apply some load to the steel, it may feel like that piece of steel does not move. But in reality, that's not true. Even for very, 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 very tiny amounts of force, a piece of material, no matter how big and bulky it is, will deform under that amount of stress. So like a very tiny amount of force will still deform a very large, strong piece of material. However, it'll just be a tiny amount. And so any time that you have stress applied to a material, you will have strain. The material will move. There is no such thing as a perfectly rigid body in the real world. And so strain is essentially just a relative measure of how much that material moves, generally speaking, in the axis that you're talking about in terms of your stress. Once again, to talk about the axis, like you've got when we're talking about pulling apart, the part is being pulled in one particular direction. And so we're talking about the stress in that direction, and we're also talking about the strain in that direction. So strain is basically a relative measure of of how much the part has changed size. it doesn't have a unit because it's a relative measure. You can kind of think of it as what percentage it has changed in size, right? Like, have you stretched it 10%, right? It's 110% of its original length and things like that. So you can think of strain as being this kind of relative measure. Um, and yeah, and so then just to kind of bring it down to just to kind of maybe possibly state the obvious here. If I apply more stress to a part, it will have more strain, right? There's a proportional relationship there. I'm not sure if it's not proportional. That's not really the right term, but basically, they're correlated, right? So if I increase stress, I will also increase strain. Um, Generally speaking, there's a couple of little exceptions to that, but um, we'll talk about those in a second. So the other thing I wanted to mention, I thought about putting a slide in about this, but I decided not to. But I just wanted to quickly mention it. Generally speaking, this kind of um, this presentation, I decided to kind of weed out as much like real world numbers and stuff out of this presentation as I could, just because like I really don't want you guys to get overwhelmed with, you know, a bunch of, like the meme of the lady and the equations floating through the air. Like I don't really want this to become that. I want this to be more about a very high level kind of building an intuitive understanding of how materials behave under stress rather than an understanding of, what is the tensile strength of this type of steel versus this other type of steels. That's not really what we're trying to do here. So if you want more information and you have any questions about some things, this topic really links pretty well back to our raw materials presentation from like week 1 or 2 of the CAD class. Um, you know, we talked about some of the common materials, some of the common steels, and a good understanding of, material strength and material properties. Linking that back to those materials could be, something that's pretty interesting. But I decided not to do it today because I think that's going too far. So if you have any questions or if you want more information, always feel free to ask. Otherwise, we'll talk about it, more in context. I can help you guys work through some of the equations and do some calculations of this stuff. Once we encounter a real world application while we're designing our robot or something, I will help you guys do actual math related to this stuff. Okay, so second to that, generally speaking, the concepts that we're talking about today apply best to metals like steel or aluminum or things like that. They do apply to plastic and like polymers as well, although there's some caveats there, and the reasons for that being that the internal structure of polymers is significantly different from the internal structure of metals, and polymers can be a little more funky and finicky. Because they're kind of a little bit more complicated materials, like atomically. Um, so this generally speaking, these properties will apply to both, but they will apply best to metals. And if there's anything that I say that's maybe a little inaccurate, it will be probably because it's targeted towards metals rather than plastics. Okay, so let's talk about a couple more terms here. So we're going to talk about yield strength versus ultimate tensile strength. So these are two properties of a material. So if I look up, I want to talk about steel 1045, right? Which is a specific alloy of steel. I can look up online what is the yield strength of 1045 steel, or I can look up online what is the ultimate tensile strength of 1045 steel, right? I can look these numbers up. I can basically go to a data sheet, get a single number that applies to this material. Now, a quick note, generally speaking, with metals especially, there is something called heat treating where I can take a material, heat it up, dunk it in oil or water or whatever. Like you guys have probably seen videos, or you guys probably seen blacksmiths working on stuff, right? They're quenching things. That this is all part of a whole complicated area of, material science called heat treating, and it's primarily with metals, but it does apply to other materials as well. Heat treating will change these strengths, the yield strength and the ultimate tensile strength, heat treating will change that. So when I talk about being able to go online and look up, 1045 steel and be able to get a single number that just quantifies this part of the material property, that is generally true, but that data sheet will apply to a specific, heat treat. And chances are, if you just go look it up, you'll find whatever the most common, heat treat for 1045 is. I don't know what it is off the top of my head, but so that's something to understand, is that these numbers can change depending on how the material is heat treated. In the context of FRC, this really doesn't matter, and so I'm leaving heat treat out of the entire rest of this presentation, basically. But that's just a quick note. So, okay, so basically, when you talk about a material, if you want to think about a material and understanding the strength of a material in its most simple state, just these two numbers are the most important things that you need to know. So basically, yield strength is the stress level at which a material starts to deform permanently. So remember that I said that anytime you stress a material, you will get strain, right? However, and generally speaking, once you relax that stress, that strain will go back to zero. It'll go back to its original shape. So if I pull on my part and I stretch it out, and then I let go, the part will retract back to its original size. Now, at some point, if I pull hard enough on that part, it will deform permanently. You may have found this with like a rubber band, right? Which is kind of an easy to understand example, where if I pull on a rubber band, it'll stretch back to its original shape. But if I pull it too far, it'll kind of turn like, it'll get like super light colored, right? It'll start out as kind of yellow color. If you stretch it too far, it kind of gets white. And then the rubber band is longer than it used to be. It's much looser, and you lose some of the stretchiness. So from a internal structure standpoint, a rubber band is actually a pretty bad analog to metals, but still, that's probably an intuitive example that you guys might have encountered. So that is the same of metals, right? As I'm sure all of you would know, like metals can be bent, right? You can take a piece of wire and bend it, or you can take a flat piece of steel and bend it, right? And it will hold its shape. But if you guys have played with like, a metal ruler or something, you can bend it a little bit and it will spring back to its original shape. And then in addition, like you guys have probably seen springs, right? Like a metal spring, a coil spring, that you see springs everywhere. Obviously, so the springs are able to deform and then spring back to their original size without being permanently bent. And so basically the yield strength is the stress level below which a material will return to its original shape. But if you exceed the yield strength, if you apply a stress that exceeds the yield strength of the material, you will see permanent deformation in the material. I've got this little chart over here. This little chart is a stress strain curve. We'll talk about this on the next slide a little bit more. But I don't know, this little chart, there's like 5 or 10 versions of this floating around the internet. I don't know where I got this specific one, but I have it on hand. This is my, like, maybe one of my more favorite renditions of this chart, but there's like this exact curve is just like floating around, and I don't know where it came from originally, but this is just a image that I yoinked. I didn't make this myself. But if you look this up online, you'll find a lot of similar charts. So the other number, this ultimate tensile strength, is basically the highest stress that the material can take before it breaks. Generally speaking, well, yeah. So the ultimate tensile strength will always be higher than the yield strength. The relationship between these two is not always the same. So like the yield strength is not always 75% of the ultimate tensile strength. There's no like constant ratio. It changes material to material, and that is actually the ratio between these two is actually an important property of a material as well. But basically, ultimate tensile strength is when I'm pulling on a part, right? And the part is, stretchy, and then I keep pulling and I exceed the yield strength and the part starts to deform permanently. But then I keep pulling, I will at some point reach kind of a maximum stress in the material, and then all of a sudden the material will kind of have this runaway, and it will deform very rapidly and then all of a sudden break. And that's basically the ultimate tensile strength, is just the highest stress you're going to get out of that material before it fails. And generally speaking, as you apply stress and you exceed or you reach the ultimate tensile strength, failure will occur very rapidly thereafter. It's not necessarily immediate, but it's very rapidly afterwards. Okay, so next slide. So let's talk about this stress strain curve here a little bit more to kind of understand what we're looking at. So what we're looking at here is basically we have stress over here on the y-axis, and then we have strain over here on the x-axis. And so remember, strain is kind of a unitless thing. So this strain here, this axis here, there's no numbers on this chart, but this would normally be like, basically just kind of like a percentage, basically, that you're stretching the material. And if you think about this as you're pulling, right, along the direction, the farther you pull, this is the stress that you're going to create in the material. And so the more you pull, as you can see from this curve, generally speaking, stress goes up. Now, there's a couple little bit of weird inconsistencies in this curve. So you'll notice stress actually goes down a little bit right after this point labeled the yield strength. And then you'll notice stress card starts going up again. It peaks where this mark of ultimate strength is, and then it does start to drop off after the ultimate strength. So that's something to keep in mind. We'll talk about that a little bit more a little later on. But basically, just keep in mind that as you're pulling on the part, your stress level is following this curve. This curve will look pretty significantly. Generally speaking, it's always going to follow this shape, but this shape can be stretched and pulled and rescaled pretty drastically based on what material you're talking about, to the point where it's sometimes hard to recognize. But this general curve does apply across the board. Once again, really does apply better for metals than plastics, but it does apply for both generally. Okay, so we talked about the yield strength, and we talked about how before we reach the yield stress of the part will return to its original shape after we release the stress, right? We release the load. So essentially, we can divide this graph here, this chart, into two regionals. We can split it right here at the yield strength with a vertical line, and everything to the left over here is what's called elastic deformation, and everything to the right is plastic deformation. Now these are very important terms when you're understanding materials and material strength. Essentially, what elastic deformation means is that in this region, before you reach the yield strength, the part is kind of stretchy, right? It's like a rubber band. You stretch it, and then when you let go, it snaps back to its original size. That's pretty easy to understand. And so elastic basically means exactly what you expect it to mean. Things are stretchy and they snap back to their original size when you let them go. The deformation, basically the strain that you see in this elastic region here is reversible, right? It can go back to its original shape. The other important feature of this region is that in general, the material or the relationship between stress and strain is linear. So you can see that right here. This is a straight line. Now, in reality, there's some, generally when you get up very close to the yield strength, you lose some of this straight lineness, that you get some curving, And the relationship between stress and strain is obviously, in the real world, it's very noisy, right? It's not, if you were to test this, if you were to generate a stress strain curve for an actual piece of material, it would be kind of a more bumpy line. But generally speaking, from a simplified point of view, of the relationship between stress and strain in the elastic region is linear. And so if you double the stress, you will double the strain, right? They are proportional to each other. Um, if I have 3 times the stress, I get 3 times the strain. And so it's very, very easy in the elastic region of the material to predict how the material is going to respond. And then once you get past the yield strength of the material, things get a little bit more um, um, complicated, because the material is kind of deforming permanently, and it's changing shape and it's changing structure, and there's some weird stuff going on. So um, basically, once you get past this yield strength, you're undergoing what's called plastic deformation, as I mentioned, and basically any strain that you have created, right, um, is like it's not reversible, right? Once you release the load and the stress goes back to 0, the part will not return back to its original size. And then in addition to that, the relationship between stress and strain follows this strange curve, and it's very hard to predict. There's no easy equation like, oh, it's the straight line, just figure out the slope of the line and do the calculation. It's a much more complicated shape, and it's much harder to kind of work with mathematically. So something that's pretty. So I want to talk about very quickly about these regions up here. So necking is basically the term where the cross section of the part rapidly decreases as the part fails. That's pretty normal. I'm going to go back to this image right here. If you think about this think about this as a metal rod, right? If I were to pull this very, very hard, the material here in the middle would start to kind of bow inwards. If you've pulled on like a piece of silly putty, that's a good example. You think about if you take a glob of silly putty and you start pulling it, the middle gets very thin, and the more you pull it, the thinner and thinner it gets, and you can even pull it to the point where you get these kind of like little wisps. Basically, metal will do that too, up to a point, and then once it necks to a certain point, it'll just crack. And essentially, that's what this region up here is. Once you reach the ultimate strength, the material really actually just starts to, the actual cross-sectional area of the material starts to decrease, and so you get this kind of runaway effect where the cross-section is less, and so the force is not spread out over as large of an area, and failure occurs pretty quickly if you keep pulling on the material. This area called strain hardening, I really don't want to get too much into this because it's not actually going to affect you very much for FRC, but this is pretty important concept outside of in just kind of general engineering. You guys probably have the hands-on experience of taking a piece of material. It could be plastic, could be metal, and if you bend it, it doesn't break, right? But if you bend it back and you bend it again and you keep doing that, eventually it will break. And so that's a property called work hardening, and essentially, people might start throwing things at me when I say this, but I'm trying to simplify this as much as I can. Essentially, a material that is hard is a material where its yield strength is very close to its ultimate strength. That's maybe a bit of an oversimplification, but I think for the purposes of what we're talking about here, that's the best way to understand it. So when you're talking about a hard material, you're talking about a material that has a very, very high yield strength in comparison to its ultimate strength. Meaning that the elastic region of the material is very large and the plastic region of the material is very small. This has different uses and things, but the thing to understand is that What happens with a hard material, if you may note, is that once you the material doesn't really bend, right? You deform it. You apply a strain, right? You apply a force. The material sees a strain, and then eventually the material just cracks, right? And that's because there really is no plastic deformation region. The thing just exceeds its yield strength, goes right onto ultimate strength, and just fails right away. Um, Whereas, maybe softer materials will bend a little bit easier. Whoa. Okay. So basically, what happens is that when you bend a material, and I'm somewhere in here on the stress strain curve. I have not reached the ultimate strength yet. I'm maybe somewhere in here. Okay. Um, and my stress levels are really high, and I have this, some, amount of strain that associates with this stress level. And then let's say that I let go of, let's say I release the load. Well, so what actually happens, generally speaking, is that this point basically becomes the new yield strength of the material. And then when I let go, the material essentially just follows this new straight line down downwards, and essentially I have created a different yield strength for the material because I deformed it. And essentially, like what I said, a hard material is essentially a material that has a high yield strength. And so basically, by deforming a piece of metal, um, I have hardened the material. And so that's what's called strain hardening. And if I then go back and I bend the material and I get to a higher stress level, and I go even farther, right? I get even closer to the ultimate strength. I have hardened the material even more. And if I keep bending the piece of material back and forth, eventually I just get the material gets so hard that you deform it very much at all, and it just cracks and it fails. And so essentially that's what work hardening is. That's what strain hardening is. Work hardening is kind of a more practical term for strain hardening, but they're basically the same thing. So that is that is a, I guess, a better, not a good, but a better explanation of the reason why, bending something back and forth makes it break. That's not necessarily super important for FRC, but it's probably good background. Okay, so all right, moving on. So I want to go back to, we talked about, oh, I realized I went back to this chart. I meant to go back to here. Okay, so we understand elastic deformation, we understand plastic deformation, we understand the yield strength of the ultimate strength, we understand all that stuff. So before we go farther, let's talk about what does it mean for a part to fail. So if I have a part, right, it's machined out of aluminum or something, right? What does it mean in the context of material strength? What does it mean for that part to fail? So obviously, generically speaking, if that part is not able to perform the function that I need it to perform, then it's failed, right? That's a pretty obvious answer to this whole problem. However, defining that, what does it mean for something to not work anymore, quote unquote? What Defining what that means in terms of like our stress strain curve here is a little bit, maybe a little more complicated. So in some ways, you can probably think of a lot of things that as soon as it bends permanently, it's basically useless, right? You can probably think of lots of things that work that way, where you never want the part to bend permanently. You want it to always spring back to this original shape and size. And generally speaking, I would say, if you don't know how to define the failure mode and the like failure stress of your part, just assume that it needs to never yield, right? That's kind of the best rule of thumb, is just if you're working with material strength and you're trying to figure out if a part is strong enough, just use the yield strength, because generally speaking, for most applications, if something bends, then basically it's useless. And so that is going to be almost always true of moving parts. So like gears, if I bend a gear teeth, that gear doesn't roll anymore. And so evaluating the strength of a gear beyond anything but the yield strength is not usually useful, because as soon as the gear tooth bends, the gear doesn't roll anymore, it can't perform its function, it's done. Shafts, same way. Shafts generally need to be very straight and very precise in order to be able to spin in bearings and things like that. And as soon as that shaft gets a little bit of a bend to it, it can bind up and it won't work. It can't move anymore. It's gone. Things like springs. Springs are very very specifically tuned to operate in their elastic region and not undergo any plastic deformation. And as soon as they undergo plastic deformation, they don't have as much spring force, or the spring rate is different, or whatever it is, depending on how it bends. It's pretty much useless at that point. However, there are some applications where you need to evaluate more extreme cases where the part will be loaded above its yield strength and it will bend, it will start to deform, and you need to control what the part will do in those situations. So if you think about the easiest example to give here is for structural or safety related things. So if you think about I don't know, a cable on a crane or something. If that cable gets overloaded for some reason, you really don't want it to just snap and drop whatever it is that the cable is holding, right? You want that. You're okay if that cable stretches a little bit. That is not necessarily. You will not drop a large piece of concrete on somebody's head because the cable on your crane stretches and undergoes plastic deformation. However, if that fails, completely and exceeds the ultimate strength of the material, and you drop something, that's very bad. And so, generally speaking, for safety-related applications or structural applications, evaluating your parts based on plastic deformation is actually also useful. Now, to put this in the context of FRC a little bit, you guys remember actually, for the students that were on the team last year, you guys remember what our frame looked like at the end of the season, right? That it had some bends in it, and that might be an understatement. It had a lot of bends in it, and so we know just from experience that frame was able to continue performing its function even though it had undergone plastic deformation. So the frame of our robot in a very, very big hit was able to deform plastically. We were exceeding the yield strength of the material. It was deforming permanently. However, that did not prevent the frame of the robot from doing its job. And so for very extreme, collisions or loading scenarios that you're not going to necessarily encounter, every match, it is sometimes okay to have parts on your robot plastically deform, where if those parts were to break entirely, like if you think about our frame, if our frame had cracked and had actually one of those tubes had split or cracked or torn, that obviously would have been very bad. The robot would not have been structurally sound anymore, and that would have been a lot of work to have to replace that tube. That being said, at the competition, if the tube bent a little bit, that really didn't affect our ability to play more matches. And so this is where structural things generally benefit from a little bit of analysis about plastic deformation, where normally you don't want them to bend. However, in extreme cases, you would rather they bend than break entirely. That's basically the point that I'm trying to make. But just to reiterate, like I said earlier, if you're in doubt and you don't know, just design for the yield strength. It's better to have a part that never yields at all. Obviously, we would be much happier if our frame never bent and didn't have any, bow to it at all. So designing for the yield strength is generally better if you don't have very well-defined, a very well-defined application or something like that. Okay, so let's talk about impact resistance a little bit. So we've talked about forces. We've talked about pulling on a rod, for example, and we've talked about if we apply this many pounds of force, we have this much cross-sectional area, how much stress is that? So that's great, and that works for a lot of different scenarios, but it doesn't basically handle every possible loading scenario. And so when we're talking about impacts, and impacts actually have a lot of um, a lot of place in FRC because there's a lot of impacts to your robot. There's a lot of shock loading, a lot of impact loading. When we're talking about a part on our robot needing to withstand an impact, um, it is not easy and sometimes impossible to define a a force, right? We can't say this thing hits our robot and it hits us with 100 newtons of force. That is not always an easy thing to determine, and it's in some cases it's not possible. And the reason for that is, with an impact, the force is not a kind of like the primary interaction. The primary interaction is actually like deceleration, right? You get an impact. One object is moving, it hits another object. The object that's moving starts decelerating, and as it's decelerating, it's applying force to the other object, and you don't necessarily know what that acceleration rate is, and so it's difficult to determine what the force is. And so, generally speaking, if you want to um, basically determine a force from an impact, you have to know what the deceleration rate is, which is not always, you don't always know. You don't always have a way of determining that. So, um, when we're talking about impacts, one thing that's a lot easier to determine is the kinetic energy of the impacting object. And so, essentially, what that means is, if I've got an object, another robot, and it weighs, 50 kilograms or something, and it's heading at me at, 5 meters per second, I can calculate what the kinetic energy of that interaction is. And basically, when we're talking about a part, maybe a piece of my robot frame that needs to withstand an impact, it is pretty easy for me to determine, or I shouldn't say it's pretty easy, it's easier to determine how much energy that part needs to absorb without failing, rather than determining how much force it needs to take. So we can actually use the stress strain curve here to determine how much energy a part can absorb, um, depending on its size. And so essentially what the energy is represented on this graph, or rather the energy density is represented on this graph as the area under this curve. And so if we want to look at, okay, how much energy can this material absorb before it bends permanently, before it reaches its yield strength, we can basically draw a line here, and we can look at this area of this triangle right here. And we can look at what is the area of that triangle, and that represents the energy that this material can absorb before yielding. Now, obviously, the actual number, the actual amount of like joules of energy that it can absorb depends on the physical size of the part, which is not represented here on this graph. Strain is just represented as this kind of unitless quantity. So you would have to actually know the dimensions of your part and do some math there before you could actually figure out how much energy the material can actually absorb. However, generally speaking, when you're looking at material choices, you're generally comparing one material to another. And so as long as you have two stress strain curves, one for each material, you can compare those two stress strain curves, look at the area under the graph, and that will tell you if one material is better at absorbing impact energy than another one is. Now, that might be a little bit hard to understand, but I should talk about something that I intentionally left out earlier. And I mentioned it briefly. We talked about the slope of this line. Now on this graph here, you'll see this little equation here called Young's modulus. This is also sometimes called the modulus of elasticity. They're the same thing. Basically, this is like I said, this is just the slope of this line. It is how much stress related to how much strain. And because this is a linear relationship in the elastic region of the material, this is a very simple equation to look at. It's just, it's essentially just, rise over run, like you learned in school. And so basically, looking at Young's modulus for a material tells you it is another data point in addition to the yield strength and the ultimate strength that tells you how the material will behave. Materials with a very, very high modulus of elasticity, this area here will be very, very steep. And even though those materials might have a very, very high yield strength, if this curve is very, very steep, the area under that curve will still be small, right? You think about it's a very long, skinny triangle, so to speak. It doesn't have very much area. And so that material, even though it may have a very high yield strength, will still not be able to absorb very much impact energy before you exceed the yield strength. And so that is another important thing to understand, is that when you're talking about impact, the relationship between the yield strength or the ultimate strength and the modulus of elasticity all play together to give you this graph that has this area underneath it. And then obviously, when we're talking about like our robot frame, obviously we know that our robot frame exceeded the yield strength. And we know that we went past this into the plastic region of the material. The area under this part of the graph here also matters, right? Depending on what stress level we achieved, right, we can draw a line anywhere on this curve, actually, and we can draw a line down, and the area under this curve will actually, represent the amount of energy absorbed. And the interesting thing here is because generally the slope, if I can call it that, of this curve here is actually quite a bit less after you exceed the yield strength. Kind of the more stress you add, you don't add, or the more strain you create, the less stress you add, or that's not the right way to say it. The more strain you add, you don't add stress as quickly, I should say. And so the curve kind of flattens off is basically what I'm trying to say. And because the curve flattens off, you essentially get a lot of area before you reach the ultimate strength. You essentially get a lot of area in this area of the chart, and this area represents a lot of energy absorption. And so from this graph, you can kind of see that materials are able to absorb a very significant amount of energy in their plastic deformation region compared to their elastic region. And so that's basically an important concept when you're talking about any design that's supposed to be, that needs to stop a moving object or an impact at all costs, essentially. Like if you've got some safety related thing where there's a guard for a machine that's supposed to stop flying parts coming out of the machine or something like that, or you absolutely cannot have that material fail in terms of it. You can't have it fracturing, but you can definitely allow it to bend, and you can get a lot of energy absorption out of that plastic deformation. So that's basically really all I want to go into in terms of impact resistance. Just the thing to understand about impact resistance is that, going back to what I said originally, the force is not well defined, and talking about energy and kinetic energy is much more accessible, generally speaking. Okay, so let's quick note about shear strength. So we were talking about, basically we're talking about tensile strength this entire time. We're talking about pulling materials. I intentionally left out compressive strength because it just complicates things, but generally speaking, the same ideas of yield and ultimate strength and everything, that all of that still applies to compressive loads. Shear strength is, I don't know, I guess it's kind of a hack. I don't really know what to call it. It's kind of the same thing where the internal forces in the material are a little more complicated than just pure tension. In the case of shear, However, it is a very, very common loading type in terms of engineering and also in FRC. And so there's kind of some rules of thumb that apply to it. So let's talk about what shear is. Essentially, shear is where I'm basically, instead of pulling along the length of the part, I'm kind of trying to cut a part in half, right? I'm kind of pushing side to side on a part. So let's say this like black pin here is the part that I'm interested in. I've got this blue part that has a hole in it. This is a cross section, by the way. I don't know if that was clear from the image, but I've got this green part that's pulling one way. I've got the blue part pulling the other way. And basically I'm trying to shear this black pin in the middle kind of along this line here, right? It's trying to break the pin in half. And then there's actually two types of shear that I've represented here. We've got single shear, which is where there's only one shear line, and then there's double shear where I've got basically if I want to break this part, I have to actually break it in two places. If I break it in one, it doesn't actually do anything. I have to break it twice. And so it's important to understand, kind of which kind of shear you have, depending on what your application is. Basically, double shear will be twice as strong as single shear because the stress is spread out across, double the surface area, double the cross-sectional area because you've got two cross sections instead of one. In general, double shear is also even a little bit more stronger because it's also a little bit more of a stable arrangement, but that doesn't really factor in here. So generally speaking, you can evaluate shear loading conditions using the exact same rules, using, yield strength and ultimate strength. However, generally the rule of thumb is reduce the yield and ultimate strengths by 60%. Take 60% of the yield strength, 60% of the ultimate strength, and use those for shear. And that's generally kind of a rule of thumb that will get you pretty close. So if you're evaluating like a pin or something on an air cylinder, and you want to know how big that pin needs to be before it'll shear, you can do some kind of back of the napkin math and just use 60% of the yield and ultimate strength to do your evaluation. That's kind of a quick thing. I think this is all we've got here, though. So let's take some questions. Anybody got any questions? I know that was a lot. I cut a ton out of this presentation as well. So I guess I wanted to add one other note. The reason for a lot of the behavior that we're talking about actually arises from the internal structure of the materials. Essentially, like metals are made up of grains, and those grains are separated by grain boundaries. And essentially, what happens is, in the elastic region, nothing is moving. The material's microstructure is just stretching. And then as soon as you exceed the yield strength, what actually starts to happen is that the grain boundaries start to slip and the grains are actually able to move in relation to each other a little bit. And that is what actually creates the plastic deformation. And then there's something similar with plastics because plastics are polymers, meaning they're made up these long chains of these molecules and these long little like strings basically that the plastic is made out of, in terms of its atomic structure, its molecular structure. Basically, they kind of act in a similar way to the grains in a metal where, these chains can slip in relation to each other and things like that, and they can deform and that is basically what causes this behavior. I don't want to go into it any more than that. So do we have any questions from the RoboChargers chat or from the YouTube chat? Looks like no. Okay. All right, let's move on. I intentionally went a little long on this one because this is a very complicated topic. This next topic that we're going to talk about is actually really short. This slide deck's like 4 slides long. So, okay, so we're going to talk about we're going to do our COTS highlight here. We're going to talk about some COTS parts. I mentioned earlier in the class that we were going to talk about this later, and here we are. So we're going to talk about chain and sprockets. Basically, we're going to talk about a type of chain. We're not just talking about any chain. We're not talking about like, chain links that are like, a chain for like a boat anchor or something. We're not talking about just any chain. We're talking specifically about a type of chain called a roller chain. You guys have probably seen roller chain. A bike chain is a roller chain. Pretty much everybody's ridden a bike, so you guys have all used roller chain. Basically, a roller chain is a type of chain, metal usually, although there are some plastic ones, um, used to transmit mechanical power. Right? It's essentially used in the same way that a gear is, where um, you're transferring rotational power from one place to another. Um, we mentioned this briefly back in our gear ratios segment several weeks ago, but the same rules apply in terms of gear ratios to chain and sprockets as well. So if I've got a small sprocket driving a big sprocket through a chain, I've got a gear ratio there, and the same rules that apply to gears apply there as well. Okay, so the physical construction of the chain is kind of important. So if we look at this image here, this kind of close up of the chain, we can see that it's made up of each link, right, is made up of some little flat plates, and then we've got some little pins and things that are kind of holding everything together. Um, there's some kind of different construction methods depending on exactly what the chain is. I believe we're going to talk about this a little bit on the next slide. Yeah. So I won't go too much into it right now. The key thing about the chain is that because we've got these pins, these little links can rotate around these pins, but they can't rotate like side to side. So that the chain can kind of wrap like this. It can wrap in one direction, can bend in one direction, but it can't bend like side to side. And so that's pretty important. It keeps the chain aligned. It keeps it from wandering off of the thing that's driving it. So roller chain is called roller chain. However, not all roller chain actually has rollers. So the chain that I have pictured here is actually what's called a bushing chain or a bush chain. Essentially, these little this little sleeve right here, you can see it's hollow. Obviously, the chain is connected in a loop, and so to connect this chain, I would take the other end of the chain, bring it around, and put a pin through here, a pin just like this. This here is called a bushing, and essentially it doesn't move. On larger chains, like I have pictured here, you've got this area here, this little barrel right here. Now this may look very similar to this, however, it's actually different. So this chain also has this little bushing part. This little bushing part is just press fit into these two plates. It's literally just friction and compression holding this in, but it's a very strong joint. And essentially, this little guy here, which is called the roller, is actually outside of this bushing. So there's a bushing going through the middle of this, but then there's another kind of ring around the outside, which is what you're seeing here, and that's called the roller. And essentially, what it does is it free rolls, and as the chain kind of rolls on and off the sprocket, it's able to kind of spin and make the chain come on and off the sprocket easier as the sprocket's spinning. Now that is only usually the case for large chain. When you get into some really, really small chain, like we use in FRC, there's not really enough physical space to build the chain that way, and so generally smaller sizes of chain switch to a bushing style where there's no roller. The bushing is just exposed like it is on this picture here. We'll talk about a little more about that in the next slide. So basically, the chain is driven by, I mentioned it already, but they're driven by these things called sprockets. They look like this. This is one of the FTC ones that we use. You can see the sprocket here, and you can see how the chain wraps around the sprocket. The teeth of the sprocket essentially go in between all of the pins or all of the bushings, and the teeth basically kind of pull the chain along, or the chain pulls the sprocket along, depending on whether it's a driven or driving sprocket. And basically, chain is good for very high torque applications. It's not really good for high speed. You can run chain pretty fast, but you can't run it super fast. We're going to talk about belts next week. Belts are really better for much higher speed things than chain is. We'll talk about that a little more next week, but generally speaking, chain is good for um, higher torque, lower speed applications. Okay, so let's talk about some common roller chains. So chain is sized based on its pitch. Basically, the pitch is the center to center distance between the pins. So from the center of this pin to the center of the next pin, that's the pitch. You'll also notice the chain. It's a little easier to get confused because the chain actually has two types of links. It has these internal links that are narrow, and then it's got these bigger links that are on the outside. It's important to note that the pitch is just from one pin to the next, regardless of what link type it is, right? It's not from here to here. It's from here to here. That confuses people sometimes. There are metric pitch chains, but they're not really very common, at least here in the US. Especially in FRC, you really don't see them at all. There is like one metric pitch of chain that matches the like 8mm pitch that's used commonly in FTC that is sometimes used, but more commonly inch size chain is used. Okay, so most chains that are used commonly, in FRC and just industrially are ANSI roller chains. Basically, ANSI is a standards organization, and the sizes of chain are governed by a standard that they control, and basically that means that a sprocket from one manufacturer that's meant for a certain standard of chain will fit the chain made by a different manufacturer. So it means that all the chains and the sprockets and everything are compatible as long as they comply to the standard. So basically, ANSI roller chains for inch sizes are sized using a 2-digit number. The first digit refers to the number of eighths of an inch in the pitch. So that might be a little bit weird, but basically, I've got some examples: 25 chain, 35 chain, 40 chain. Basically, the first digit is like a 2. That means there's 2/8 of an inch, or the pitch is 1/4 of an inch. Okay, 40 chain has 4/8 of an inch, or half an inch, right? That's what the pitch is. So the pin to pin distance is half an inch. 35 chain, it's 3, which is 3/8 of an inch. That's the pitch. The second number is basically either just a 0 or a 5. I'm not 100% sure why it's a 0 or a 5. I don't know if the other numbers mean other things, but 0 or 5 are the only common ones used. Basically, 0 means it's a roller chain. Like we mentioned before, this construction thing where it's either just the bare bushing or it's got a spinning roller on it. A 0 means it's a roller chain with a roller, and a 5 means it's a bushing chain, which means it's just a non-rotating exposed bushing. Basically, in FRC, the most common size is 25 chain, and that applies to FTC as well. Obviously, it means that it's a 1/4-inch pitch chain, and it is a bushing chain. Obviously, this is a little bit more on the smaller side. Industrially, these chains go up much larger sizes to handle high load industrial applications. In the case of standard ANSI roller chains, 25 chain is very small, but it's pretty well suited for FRC and FTC as well. Basically, because it's a small size, it's going to be a bushing chain. It's not going to have rollers. Now, 35 chain is also somewhat common in FRC. If you've got to do something very high load, 35 chain is a lot stronger than 25 chain. Obviously, it's also a lot heavier. Chains are generally steel, so they get pretty heavy very quickly. Some teams have used 40 chain for certain applications, but it's not very common. And then any size larger than that is just never used inside of FRC. Okay, so let's talk about sprockets. I've got 2 slides for sprockets here. We've got hub sprockets, and then we've got plate sprockets on the next slide. So essentially, a hub sprocket is pretty simple. It's basically just generally a machined piece of metal, but they can also be plastic as well. We use some plastic ones for FTC. Generally speaking, a hub sprocket just has this kind of thick area on it. It's got the thin area around the edge with the sprocket teeth on it that engage with the chain, and then in the middle it's got this area called the hub, and it's basically just a thicker area that kind of widens out. It's got the kind of the thick area here, and then that thick area has a torque transfer interface that allows you to put the hub sprocket on a shaft and transmit torque through it. In FRC and FTC, generally speaking, the torque transfer interface is a hex bore. All the ones I've shown here have a hex bore, but you can also get sprockets that have a keyway or for a D shaft, or there's other torque transfer options available. Basically, these hub sprockets, the ones that I'm showing here, are meant specifically for FRC and FTC. They're made by various suppliers that supply parts for these programs. However, you can also get hub sprockets that are just standard off the shelf that are meant for more kind of generic, maybe industrial applications. Obviously, I'm showing up here, I'm showing a double sprocket. It's got actually two sprockets side by side. This is all one piece of metal. Generally speaking, this is used, this is more specifically designed for like a drivetrain, where I need to basically chain a bunch of things, like multiple wheels in a line on the side of my drivetrain for like a tank drive. And so these double sprockets are relatively common inside of FRC. Okay, now plate sprockets are, similar to hub sprockets, where they've got, the relatively thin piece of metal, and then they've got the, sprocket teeth on the outside. However, they are completely flat, as the term plate would suggest. They're completely flat, and they don't have a hub. They do still sometimes have a torque transfer interface. They've got some bolt holes or some keys or a spline. They've got some sort of torque transfer interface. However, generally speaking, the bolt holes are the most important feature of a plate sprocket. The bolt holes are generally used to bolt a plate sprocket to a structural element or a hub that's driving something larger. Generally speaking, a plate sprocket is never the driving sprocket, or you're never attaching a plate sprocket to a motor. You're always driving the plate sprocket, and so the plate sprocket is attached to whatever it is that you want to drive. So one of the best applications for a plate sprocket is if you want like a high torque arm, or you want to pivot an intake or something like that, you would attach the sprocket to your structure directly. You wouldn't even use a shaft as a torque transfer interface. You would just attach the sprocket directly to your structure, and then you would pivot your structure using that sprocket. If you guys want an example of what this looks like, you guys can look at our arm from our FTC robot last year. We essentially did the same thing. We're not actually using a shaft there to transfer torque. We're just driving the sprocket directly into the structure of the arm. Okay, and that's basically it. I'm not really going to go into designing with sprockets and chain in this. We do have a project at the end of the CAD class that goes into that. I will say in the CAD videos for this week, I did say something inaccurate when I recorded the CAD videos. I said that this week we're finishing up this project, which is true, but I said that next week we'd be starting a different project. However, that is not true. I forgot my schedule for a second, and I realized next week we're doing a little more of a tutorial thing in CAD, and then we have one final project, and it's all bundled into the last week of the project, or the last week of the class, I'm sorry. So that was something that was inaccurate. But in that last project, we will talk a little bit about how to design with chain. We're gonna kind of lump chain and belt into the same project, I think, just to kind of show it off. But yeah. So anyways, any questions on sprocket or chain, or questions about material strength as well, if you guys thought of something you didn't think of earlier? Okay, if we don't have any questions, I don't see anything in the YouTube chat either. So if we don't have any questions, that's going to be all for this week. Go ahead, and the CAD video for this week is up on the RoboChargers YouTube channel, so go ahead and check that out and follow along and try to finish up that project. Basically, after this CAD class is over, we've got 2 more weeks after this week. Once the CAD class is over, we are going to be getting very close to the FTC season starting. We've got basically, oh, we've got a couple more weeks and then we're into August and then school starts. We've got some kind of initiation stuff going for the team. And then, the beginning of September, I don't exactly know when FTC kickoff is, but once we get through August, we're going to be right into FTC season. So there's not going to be a lot of time. You guys are going to be a lot more busy once you guys get back to school. So I would like to see you guys try to make sure you get caught up. And if any of you guys don't have, you guys are not up to date on all your CAD projects, I'd like to see you guys try to get all of those finished by the time we get done with the class, so that you guys are up to speed when we get into FTC and we start doing some actual real design. Any last things before we end here, guys? Alrighty. Thanks for coming. I will see you guys next week.